Okay, so it's a real pleasure. We've made it to 4:15, and our final speaker is Peter. I'm going to pronounce this wrong. Vergeer.
Vergeer.
Yeah. Okay, I pronounced it wrong. Yeah, but you pronounced it very nicely.
That's way of the heart.
And he's going to talk about a Bayesian network for glass evidence evaluation at the activity level.
All right.
Take it away.
Okay.
I don't think that works.
You have to use the arrow keys.
Only with the computer.
Yeah, that seems to not work.
Okay. I'll be. Can everybody hear me? Okay, good. So yes, I will be talking about a Bayesian network for glass evidence. So this is an expert system. It's for glass evidence. I'm a forensic statistician working at the Netherlands Forensic Institute. And this morning we learned that well, I'm not an expert on glass, so I should not be talking about the Bayesian network for glass evidence. Luckily for me, my colleague Andrew van Es is a glass expert, so we work together on this. So this is a joint collaboration. Okay. So first of all, the basis of our work is that we start with numerical likelihood ratios at the source level. So we have, for example, a piece of glass found on the clothing of a suspect. One piece with a crime scene, broken window, and we want to know if this piece of glass originates from this window. So we have two hypotheses: it originates from the window or it originates from an arbitrary different glass source. This is the likelihood ratio at source level. Now we assume for this talk that we have numerical values for that kind of question, which is already quite a difficult question. But now we just assume we have numerical values and we go to the next level, to the activity level. So at activity level we can look at multiple particles that are found on this garment of the suspect. And how did they get there? That's the relevant question at activity level. And intuition says that, well, if you find more matches, then we should get a larger likelihood ratio. But how large? What is the relation between the number and the likelihood ratio? If we get more trace particles with only one match, then the likelihood ratio should be smaller. The chance of a coincidental match when you have many trace particles gets larger. So how small and what is the relation? So the goal of this talk is to get to numerical likelihood ratios, to have a quantitative Bayesian network to get to numerical likelihood ratios. Hypothesis I will address at the activity level. HP, the garment has been worn during striking of the window by the person who struck the window. That's quite a complicated sentence. Why is it so complicated? I will come to that. HD, the garment had no relation to the incident. So why don't we just say, why don't we do this at the person level? Well, that is because we address it at the garment level, since the relation between the garment and the suspect doesn't have to be direct. Sometimes this garment is found laying somewhere in the bushes. We still have to connect it to a suspect, so we address it at the garment level. And also I have to say that at the moment we do not consider alternative explanations for the glass found, such as secondary transfer or primary transfer due to innocent reasons. Okay, let's see some typical case data that we find in the Dutch casework. We have a number of particles, say 4 that are found to match, let's say pairwise likelihood ratios with the reference particle much larger than 1. And then we have a bunch of other particles, let's say 6, that are found not to match. They have likelihood ratios close to 0. The latter are then assigned to come from some background population of particles. So only the source of the matching particles is actually disputed. The background particles are taken for granted. The source of the matching particles is disputed as either from the reference pane or also from a background population. And pairwise comparison of the other 6 particles reveals a grouping of, let's say, 3, 2, and 1. Now you might wonder, well, if this is the problem, it's already solved. It's already done. If you are into glass, then you're probably familiar with this work, Forensic Interpretation of Glass Evidence by James Curran, Tasha Hicks-Champeau, and John Buckerton. And they have presented a very nice formula for this kind of problem. So what am I doing here? It's all been done. Yes, this is a classic. If you're interested into glass, I recommend you to read this. This is very, very nice work. Oh. Yeah.
Very lucid.
Huh?
Very lucid.
Lucid. So what's new in this talk? Well, in the Netherlands we have a very different distribution of glass particles found on clothing. We find in general more glass particles and a larger variety of sources. The other one is that the amount of glass particles is often too large to measure them all. And these formulas are designed for when we have measured all the glass particles on the garment. We only have samples in many cases. So you may wonder, why do we find so many particles on this garment anyway? Why don't we just find a few? Well, I guess that's because most of the things we get sent in, most garments are from, I would call them serial burglars, professional burglars. They tend to do a lot of these kind of crimes, so you find a big background distribution. Okay, so the outline of this talk. I will present the general base net for this type of problem. Then I will discuss what I call the classical solution from the book on forensic glass evaluation, and respective background model that is assumed. How this classical background model is informed by data. Comparison to our data and why our data is different. So then why does the classical background model not work for us? And then I present an alternative background model. We propose to model this by what's known as a Chinese restaurant process. I will present parameter and model fitting and first results in a typical case and end with a conclusion. So this is quite a lot, and I hope you stick with me. It's the last talk of the day, I know. But try to stick with me, because this is work in progress. So I'm also very curious about thoughts, comments, ideas. Let's see what comes out. Okay, a general base net for this type of problem. So this is a general base net. The first node here is the hypothesis. So the garment has been involved in this crime, whether or it has nothing to do with it. Then we have a node which says here transfer, persistence, and recovery. So it determines how many particles are found at the garment from the reference pane when the garment was involved, and when the garment was not involved, you will find here zero particles from the reference pane. Then, let's see, there's an assumption. Here's the background distribution that is modeled. And I haven't defined this yet, I will specify this later. But the assumption is that the background distribution is independent of the hypothesis. So it doesn't matter which suspect we are looking at. It doesn't matter whether the suspect was actually involved in crime or not. The background distribution is the same. So this means that we can learn the background distribution from other cases. And this is quite a general assumption in glasswork. So we will use this here. And there are two evidence nodes, namely the number of observed particles on the garment, and in the end only the matching particles, the origin of the matching particles is disputed. So we need measurement results from the matching group and compare them to a reference particle in the end here. And one more remark. The number of observations here and the number of background particles are deterministic nodes, ones and zeros inside, because this one is just the sum of the particles that come from the reference pane and the number of particles that come from the background. And the number of particles that are from the background are determined by, well, the background configuration, the grouping in the background is just the sum of those particles. So I'll discuss the other nodes. Transfer, persistence, and recovery, I mentioned it briefly. So its parents are, is the H node, the hypothesis node. And if the garment has no relation to the incident, then the number of particles coming from the reference pane is just 0. So the probability TPR 0 is 1 and greater than 0 is 0. The other one, transfer, persistence, and recovery, given that HP is true, it has some probability distribution, and we will find with some probability 0 particles to the number of particles we have observed. And this probability distribution, there is a very nice PhD study by James Curran, publication in Science and Justice, for a model that gives you the probability distribution as a function of the number of particles. But in practice, the only probability that is important here is the probability that the number of particles is equal to the amount of matching particles found. Why is this? Because when we would assume that we have less particles than the number of matching particles observed, there is more coincidence in this model, because we have then the rest of those matching particles are assigned to the background, and that's an extra coincidence factor. So this does not contribute to the numerator of the likelihood ratio, or a very small amount. So we only have actually two states for the TPR node: 0 or equal to the number of matching particles observed. Okay, then there is this node, and that says the group assignment of the matching group. So either from the TPR branch or from the background. And here we just defined the number of particles and the grouping. But in this case we are really going to say, okay, particles A, B, C, and D were the matching particles. What's the probability to have them in a group of, say, 4 out of 10? Well, that's just related to the number of combinations. So 1 over the number of particles divide 1 over this term, the number of particles observed, over m, the number of matching particles. But if TPR is 0, then all the particles are assigned to the background. Then it becomes a little bit more complicated, because again we have, let's say, then we must have a background group of, in this example, 4 particles, because we found 4 matching particles. So again, it's the number of combinations to place these 4 particles into this group. But then if we have more groups in the background that have the same amount of particles, we have a larger probability to address these 4 particles, namely the number Z accounts for the number of groups that are in the background, which have the same number as the number of matching particles. So Z is the number of groups with size m. Okay, and then the last node, the measurement results node, and it has 2 states. It has as observed or not as observed. What I mean with measurements is a physico-chemical measurement, like a refractive index, or in our case, from a laser ablation ICP-MS apparatus. It just gives some physical measurements. And we have 2 probabilities here that are important. One is to have them as observed when m, the matching particles, are from the reference pane. And this is equal to the numerator of the source level likelihood ratio. And we have another probability that is important, namely to have the observations given M are from the background, which is the denominator of the source level likelihood ratio. So this contains the source level likelihood ratio information. Okay, so now what I'm going to address in this talk is the background. So what is the background configuration? Well, it's the number of groups and group sizes of all the particles that are addressed to come from the background. So for example, we have here 3 groups with the number, the group sizes also indicated. And we need to get a probability model for this. Okay, so that's the probability model. I will derive it for the classical solution and the respective background model. So the classical model presents this formula. We have the source likelihood ratio, and then we have here the transfer, persistence and recovery of the matching particles. So that's the one probability, TPR probability. And then here there is the probability of observing the number of background groups that is equal to the number of groups observed minus 1. So this depends on the background probability distribution. The number of observed groups, that's the term that depends on the background probability distribution, and the other 2 terms as well. These are parameters derived from the model for the background distribution. And how does that work? Well, this model looks like this. So we have this background configuration, and it is determined by the probability to observe a certain number of groups, and these probabilities are conditionally independent given the number of groups, and these are the probabilities for the group sizes. And in the end, there's the bookkeeping note, which just says, okay, we have to, the group sizes add up to the number of particles in the background. Okay, so we have a prior distribution for the number of groups, and actually when you think about it, only 2 states are important here, because either 0 particles are from the reference pane, and then the number of groups is the number of groups in the background plus 1, namely the matching group, which is also then attributed to come from the background. And the other one is when the matching group is attributed to come from the reference pane, so we just have the groups that are left over the background group. So there are only 2 states important here. And given the number of groups, these are conditionally independent, and the probabilities that are assigned here are just marginal probabilities for the group sizes. So why is this conditioning then here? Because the probabilities in these tables are all the same. Well, that's not really true, because when let's say the number of groups here is 2, then this group size is just set at 0, and these may vary as the marginal distributions of the group sizes, because we have only 2 groups.
This model is assuming there are at most 3 groups.
This, yeah, so when we observe more groups, you are right, I forgot to mention this. When we have more groups, then the number of nodes expands by the number of groups we have observed. Yeah. Yeah. Yes, as many size group nodes as the number of groups observed. Yeah. Okay, so this background model does lead to the classical formula, and how does that work? Well, as I said, there are only 2 states important here. For the denominator of the likelihood ratio, the number of groups, they're all from the background, so the number of groups is equal to the number of groups observed. So that's here the denominator of the likelihood ratio. Then there's a term in the numerator of the likelihood ratio, namely probability that the number of groups is equal to the number of groups observed minus the matching group, because that comes from the TPR. And then there are 2 terms left. Probability that the group size is equal to the matching group. Why is this term left over? Because the other group sizes, probabilities for the other group sizes, are they're from the background anyway, so they are present in the numerator of the likelihood ratio, but also in the denominator, so they cancel. So there's actually only one added group in the denominator, namely that is when the matching group is attributed to the background. So that's the only probability we need. And then there is the number of observed groups, and that is because, well, let's say we have group sizes of 3, 2, and 1, then there are a number of combinations that lead to these group sizes. And this is the number of combinations for this 3, 2, 1. But when one of those groups is a matching group, then for the numerator of the likelihood ratio, it's just one of those groups left out, a number of permutations for this. And when you divide this, you get indeed a number of observed groups. Okay, so how is the classical background model informed by data? So we need marginal distributions at the Garmin level of the number of matching groups and the group sizes, and I just put up an example here. This is data from a population of persons involved in glass-related crimes. And the black boxes show here the distribution of the group sizes observed. And you see that it's a very strong decaying function, it's an exponential decay. And this is the way that you can get data to put into this to the background model. But we have different data, because the data I showed you was at the garment level. We have sample data. Here are the number of particles we found on the garment, and it can go up to, well, here our expert says it has more than a few hundred, so I just truncated it at 200. It can be even larger. And this is the line y is x. So if we would have been able to measure them all, then they would have all laid down on this line, because this is the sample size. So our sample size does usually not go over 20 particles, and that's because measurements are laboratories. Yeah, just a lot of work to measure them all. So we have samples. And extrapolating from sample information to what happens in a finite-sized population, extrapolate the grouping probability of this finite-sized population at the Garmin level, that is a very difficult job. There's some work published on this. You can read this reference. The uncertainty, when you have these kind of sample sizes, uncertainty on the estimates of the group sizes is huge. So this is actually, I think it's a dead end to use these data to get to these probabilities. So we have, for the classical model, it's based on estimates at the garment level. Our data is based on sample data. The classical model, we have probabilities versus the group size, which decays rapidly. Our model, our data show that the probability versus the group size actually decays rather moderately. We have a lot of large groups in our data. Is this because the way we separate the groups is not very efficient? I don't think so, because the classical model, this grouping was based on a refractive index. Ours is actually with a more discriminative method, grouping based on laser ablation ICP-MS. So I think our grouping is pretty accurate, and still we have these large groups. Okay, so why does the classical background model not work for us? Okay, so we'll just put down an extra note in this network. This is the classical background model. We here have the configuration of our sample, and well, it's easy. I mean, the configuration of our sample is just drawing balls from the population without replacement. We just pick a few. It's a multivariate variate hypergeometric distribution. So it's easy. Well, we have two possibilities for the sample configuration. Namely, we have our particles that are attributed to the background anyway, and then we again have these matching particles in our sample which are attributed either to this one or to those. But we can have many configurations here that are in accordance with our sample, because our sample is only 20 particles, and well, sometimes we have 100 particles at the garment level. So there are many ways for our configuration here to be able to yield us our sample. And in the original derivation of the classical model, these probabilities here cancelled nicely, but this does not happen when we have our sample here. And well, that is because, let's imagine that we find from 10 particles at the garment level, and we have a sample of 2 and they both match. Then, well, we could have here, let's say all the particles are from this same group. Then we have one group and a group size of 10. We could also have 2 groups, 9, 1. 3 groups, 8, 1, 1. And so on. This could all deliver us our 2 matching particles in the sample. So the number of groups here is a weighted average of these number of groups that I just said. It's a weighted average. And also the number of observed groups here becomes dependent on what we, on this probability. So things get pretty messed up here. So this does not work. We cannot cancel all these probabilities here. Okay, so can we just do the full calculation? Well, if we have 100 particles, the number of ways to get groupings of them is 190 million. Okay, that's quite a lot, even for Bayesian network software. So, no. So we have 2 problems. The number of states explodes. Probabilities of states cannot be estimated from our sample data. Okay, so we would like to propose an alternative background model that is known as a Chinese restaurant process. What's the general idea? To regard the configuration of particles at the garment as a sample from a broader population. So this is the particles at the garment, and they are drawn with some probability distribution from some population. And then we again draw from the garment a random sample that gives us our sample that we actually measure. Okay, but there's one subtlety. We don't see what's going on over here. We only have the number of particles. So actually, we had this, but we don't observe this, the properties of this sample. So actually, we just have a smaller sample here with the same probability distribution as the larger sample, because this is a random sample from this one. So it's just like drawing 20 balls from a vase and then taking at random 10 of them and only observe those 10. So you can just leave out the other 10 because you don't observe them anyway. So it has the same probability distribution as this one. Okay, so what we can do then is replace the whole background stuff with the parameters of the probability distribution. Because these determine then the configuration of our sample. So we don't have anymore the need for a garment background distribution. So what probability distribution for the particles on the garment of a specific suspect? Because it has the same parameters as the sample, so I'll discuss what probability distribution this is, because it has the same probability distribution for our sample. How does a person collect gloss on his clothing anyway? Well, let's just say, well, you live somewhere and there are a lot of windows around and glassware in your cupboard and stuff. So somewhere there's some prior for all those kind of glass sources, and there are a lot of sources. So I will just say there are infinite many sources. And these priors can vary a bit. One can be a bit larger than 2 and 3 and so on. And then this guy goes around. Maybe he's a serial burglar and he goes around and one source he comes very close by. There's some transfer persistence and recovery. Another source, transfer persistence and recovery. And all those sources have their own specific transfer persistence and recovery. And maybe the persistence is related because, it's determined by the way he behaves, whether he washes his clothing and stuff. So this gives a lot of parameters. If you want to model this explicitly, this just gives you a million of parameters. That's not doable. However, what may be a possibility, what we propose here, is to look at the posterior distribution of all those probabilities at the time of arrest. So let's just say that, because of his behavior, the first source has the second largest probability to be found at the time of arrest. And the second one is here, is in the order. The third one is first. Okay. And the idea is now to observe the probability to observe a particle on the garment from a source X is determined by this probability vector. And the probability to observe it from source 3 is just this probability space. To observe it from source 1, this probability space. And each particle from the garment is regarded as a new draw from this probability vector. Okay, but we don't know this probability vector for a specific case. That's true. So we treat this probability vector as a random vector of ordered probabilities with infinite length. And this is directly related to a random vector W of unordered probabilities, which is constituted by, in analogy to a so-called stick-breaking process. So there's a model that can actually describe this, which I will introduce now. So let's just say that this random vector W, that the sum of all these probabilities in this vector is again 1. And the probability to observe a particle from the first source is defined by this probability space. And for the second source, then you can do what is called stick breaking. You just cut off this part and you define again this probability space, and it's again a Bernoulli trial, this probability space versus the rest. So I call this V2. And then actually when you convert it to the whole probability space, W2 is 1 minus V1 times V2.
V1 should be W1? Oh yeah.
Yeah. So to make it complete, V1 of course is equal to W1 because there's been no stick breaking. For the third one, again you do the stick breaking, 1 minus V1, 1 minus V2 times V3. Okay, so in that case you can constitute indeed this vector W. And when you go on, fourth, fifth, and so on, it's this recurring formula which gives you the probabilities. It's not random yet, this vector, but the randomness is actually in the V's, because there is a nice prior model which says that the V's are beta distributed with two parameters, alpha and beta. And when alpha is between 0 and 1 and theta is larger than minus alpha, and this is known as a two-parameter Griffith-Engen-McCloskey distribution. And there's a nice article by Julia Sereda. She has casted this in a Bayesian network. For example, let's say the observed grouping of 5 particles is 1, 4, 5 in one group, and 2 and 3 in another group. And this is also known as a partition of 5. So this is the observed grouping. Here are alpha and theta parameters. And then here we have, well, let's say a bunch of p factors according to our beta distribution of the v's. And the S states here, they are identically distributed according to the p vector. So these are the independent draws of our glass on the garment. But we only have the observed grouping here, so we don't have actually the ranks of the S nodes. We don't observe the ranks. We only observe the grouping. Okay, so what is the probability of an observed grouping? Well, when you can model it like this, then this observed grouping actually only depends on the probability for an observed grouping only depends on the parameters alpha and theta in the following way, and that is defined by a Chinese restaurant process. The analogy is as follows. Here's a customer to a Chinese restaurant, and the customer is, you should think of the customer for the glass case as one glass particle on the garment, and it can be attributed to a certain source, and that is in the analogy that is a table in the Chinese restaurant. So the first customer comes in and just picks a table. That's the source of the glass. The second customer sits at the same table. The third customer and the second customer as well, they can also choose to sit at a new table. And the fourth customer maybe again chooses to sit at the first table. So what's the probability that the customer chooses to sit at a certain table? So this new customer, the sixth glass particle, can either be table 1, table 2, or table 3. So the probability for this customer to sit at a certain table I is when he opens up a new table, it's defined by this theta and alpha that we have encountered in our V factors, the beta distributed V distribution. K here is the number of tables that were already there, and is the total number of customers that were already there. And when he sits at an existing table, then it's proportional to the number of people that are already present at this table. And there are some nice things about this probability distribution. First of all, when we want to have the joint probability distribution, then it's just multiplying all these conditional probabilities for the first customer to sit at a certain table, second customer, and so on. And also there's a nice feature, namely the joint probability distribution does actually not depend on the order of entrance. And that's good news, because for our glass on the garment, well, we wouldn't like to have that this probability distribution actually depends on the order that we measure the particles. Okay, so when we assume this p vector for our 2 minutes, okay, parameter and model fitting. So what we have is a lot of cases, and we have, in these cases, we have observed groupings, and these are all determined by a Chinese restaurant process, and we want to actually to learn something from these cases for our new case. So we assume that they have the same alpha and theta here. Else we could never learn something for different cases. So they have a unified stick breaking prior. So then we can get maximum likelihood estimators for our data, and well, maximum likelihood estimator for alpha is 0.54, and for theta it's 0.6. But there's quite some. It's not a very steep curve, could say, especially in this direction. Do we have a good model fit with those maximum likelihood estimators? Well, what I did here is resample our observed data, resample with the same sample size as our observed data, and then look at the quantile of the log likelihood of our data set. And you see that it's pretty good. It's the 60-second quantile. So this means that what we predict as a log likelihood is actually within the spread of log likelihoods that you would get for these kind of parameters. So we have a good fit. Maybe there's some overfitting here, and for that we do a sensitivity analysis. The only thing important here is now that we have this grouping of the background sample, which is determined by this Chinese restaurant process, and we'll just skip this. First results in a typical case. So this is a typical case. We have a clustering here, so these are all background particles, these are matching particles, and this is the reference particle which cluster together. And we get a log likelihood ratio based on our maximum likelihood estimates for alpha and theta of 3.89, and it varies, well, just a little bit. So we vary the alpha and theta according to our log likelihood ratio graph here. So it seems to be pretty stable. Conclusion: when evidence in glass analysis consists of measurements on sample, the traditional formulas become unfortunately inapplicable. Viewing the glass particle on the garment as a sample from a broader population allows for modeling of this background distribution as a sample from the sample. We have modeled it here by a Chinese restaurant process. Sensitivity analysis of the likelihood ratio reveals a small effect that is very nice. So I've come to the end of my talk, and it's time to have some other glass involved and questions.
I've got quite a few simple questions to ask you actually. First of all, how can you put infinity into your formulae when the populations of glass are known, presumably? Because I've always been told that glass has population data, whereas many other things don't, so I can't see the relevance of infinity. And then also, you're using laser ablation, ICP and MS analysis, which means you can identify things with great specificity, presumably. Wouldn't it be better to look for fragments that have this, that can match this the specificity, rather than looking at it as a general sample?
Shall I start by answering the first question? And then
Yes, yes.
Okay,
No.
all right. So the first question, there are maybe a finite number of glass. So I guess you are talking about the way it's manufactured, that there are a finite way of the batches of glass. What I'm talking about with glass sources is glass in houses. So the number of windows and the number of cars, the number of windows in cars and in houses, and that's a very large
It's still
number.
population data.
Yeah, but it's
Still-
a large number. So
I know it's large, but
approximate.
it's still there. It's not infinite.
It's not infinite, but
No,
I think
you
it's
put
a good
infinity
approximation.
in your thing. Also, you're assuming that the distribution of the glass populations is random, are you? But if you have a burglar,
Yeah.
a persistent burglar, he's going to be targeting certain types of glass. So there might be a preponderance. Well, I mean,
He's going to be targeting certain kind of houses. I
yes,
agree.
but probably
And I-
with certain types of
I
glass.
discussed this with the glass expert, and it depends on the age of the houses. New houses
Don't
tend to
use
have
the same glass in
similar
cars as you do
similar glass.
in houses,
And
surely.
in cars they have well, cars are randomly distributed, you could say, so the windows vary there. So a serial glass burglar picks out a random population of glass, and a serial house burglar depends on the type of houses he chooses, whether it's a random, whether you regard it as a random.
I can't see how it can be random in reality. I just can't see that.
It's because the way the glass is distributed over the houses.
It's random.
It depends on the aging of the houses. So new houses that are built, those
Not random.
glasses are very similar. So it's not random.
Random.
But when the houses become older, then it becomes random.
No, I don't believe it's random.
Okay.
But he's modeling the randomness of the numbers of particles from each of different sources.
But is he?
Yes.
Yeah. So what
I mean, the background
the Chinese
glass.
reference process is about indeed about the number of particles from the different sources.
And not what those sources are.
Yeah, I'm very uncomfortable with this.
You know what, that might be a good, you might be able to
Yeah.
speak to him during the drinks on that one.
Yes.
Yeah.
But have we got another question? Oh, okay, another question.
Well, another problem I have, you talk about your reference sample from the scene, but we'd never say it was from that. Or we'd say, or from another place.
Yeah.
You can't assume just because you've got a match with that glass type,
Yeah.
it's from the incident.
No, I don't.
That's very dangerous.
No. When I speak about match, then they are similar to those reference. So the LR, the source LR is larger than 1, but that's the origin is disputed.
Yeah, that's
So
right.
I'm not assuming that they are from.
But-
But why do you
Well,
use
that's
the
right,
word
but you-
match?
Huh?
Why do you use the word match?
Because it's an easy way to say that the likelihood ratio is larger than 1. But that's how I define it.
You have problems in the British court.
Yeah, in court that would be difficult to use.
We are not in court. So
No,
I
but this is a
wouldn't use
forensic,
it,
this is
uh,
interpretation of forensic.
I wouldn't use this word in court because I know that it leads to a lot of misunderstanding. Because then immediately people will think, oh, it's from the reference.
Okay, I think that we're getting to the end of the. Oh, one final very quick bit.
Quick and unhelpful. So first thing, the very fact that a person has lots of glass on his clothes means that he's probably, unless he has another explanation, that he's a professional burglar.
Yeah.
So this is in itself a very important evidence,
Yes.
I think. And if we are about deterrence, then I don't even care if I put him to jail for the right burglary, right? That's from the comment.
I think a judge would argue differently. But I understand the remark. Now, but also, I mean, the likelihood ratio for a serial burglar becomes smaller because of those many groups that are found, but the prior obviously becomes larger.
Thank you very much. We now have